All right, APChem peeps, this is where it gets messy. It's this one. Yep. It says determine the pH of a solution of 1.20 molar NaF, or sodium fluoride. They give us this Ka value of HF, which doesn't look quite like this. But when I look at this, it's sometimes like, what are they talking about? This doesn't look like an acid. It doesn't look like a base. So what's going on? Well, just like all our other problems, we start off by writing out a net ionic equation. But the other thing we need to consider is our solubility rules and see if it compares to any of our strong acids or bases. Okay? So we have this compound NaF. Okay? First of all, it contains Na. So it does follow a solubility rule. So it will completely dissociate in solution. So even though when we see NaF and they say it's a solution of it, it's aqueous, really we need to think of it as Na plus, aqueous, and F minus, aqueous. Okay? Because this Na is part of a strong base, it doesn't contain the OH minus ion. This part does not affect the pH because there's no base connected with it. Yep, that's fine. And so there's no equilibrium that comes out of that. So we don't have to worry about Na. But this F minus part, notice that the fluoride ion does not appear in our solubility rules, does not appear as a base. It does not appear as part of our strong acids, okay? Which means that it does act as a weak attractant of protons, or a weak, in some other cases, you could have weak acids or weak bases and things like that. This will count as a weak base. And the other hint they gave you is that solubility or equilibrium constant for HF, it is actually a conjugate pair with HF. So we're going to kind of use that, but this is what we're starting with. I'll show you kind of how to write out that net ionic equation. Let's do that first, because that's going to direct everything else for us. So we have this NaF, aqueous, and it reacts with water, liquid, or interacts with water. Because we're dealing with something that's weak, because we identified this weak part, that it's not part of the strong acids, it's not part of the solubility rules, it is going to act as either a weak acid or base. But before we get there, remember that this NaF is really Na plus, aqueous, and F minus, aqueous. And because it has sodium, it will completely dissociate into this. So this isn't how we want to start it. We want to start it this way. Plus H2O, liquid. Like we said before, the sodium, because it's will completely dissociate with anything, it actually doesn't take part or interact with water. It just stays as Na plus, aqueous. And it does that with other stuff too. It doesn't really react with them. And so, but because of that, it is considered a spectator ion. I'm going to cross it out right now so that we can actually focus on this. And so the F minus, it's going to interact with water, but it can't be an acid because it has no protons to give. It has to take on a proton or take on a hydrogen atom. And that's where it will form HF, aqueous. So that's where this came into play. And so it forms that. But when it takes that hydrogen, it came from the water, we are left with OH minus. So when we kind of think of this F minus, when it's dissolved into water, it interacts with water and actually forms a basic solution. That's because of the presence of this OH minus. Yes, it did make a weak acid, but the pH is based off of either H plus or OH minus, and here's the OH minus. It is going to be basic. Okay? So that's kind of what our net ionic equation is. And we're going to rewrite that so that we have a clean place, and it's going to be easier for you guys to kind of see. So plus H2O, liquid, yields back and forth between, we said HF, aqueous. And this doesn't completely dissociate because it doesn't have those solubility rules, doesn't have Na, Li, K, NH4, all that stuff. And it's also not part of a strong acid, so it doesn't completely dissociate. And it sticks together like that. And then it plus the OH minus that we said. And all right, so here's our net ionic equation. And now we go back to what's our next step? We go back to our scheme. We wrote out our net ionic equation. We do not have to do stoichiometry because we have a weak thing, but we are not mixing it with a strong thing. There's no stoichiometry. Instead, we got to do the ice table. And so we got to deal with the Ka or Kb expression. Yep, we'll get to there. But here we go. We're going to start off with our ice table. And our concentration of F minus, because it came from this NaF, it's completely dissociates into 1.20 molar Na and 1.20 molar F minus. And that is our initial concentration of the F minus, okay? Because it splits into 1 mole and 1 mole of that. And water, don't have to worry about. We're going to assume that these concentrations start at 0, even though, remember, this OH minus concentration, it's about 0. It's really 1 times 10 to the negative 7th in neutral water, but because it's so much smaller than everything else, we can assume that it's negligible. And our change, we're going to be forming products, so we're going to subtract X, plus X, plus X. And it's all just plus 1 or minus 1x, plus 1x, plus 1x, because all my coefficients are 1. That's nice. But then at equilibrium, I have 1.20 minus X, and here I have X and X. Nice. Now comes for the stinky part. And because they gave us, they gave us Ka of HF, and it's kind of like, oh yeah, I could use that. But we can't use Ka for this problem because in here, this equilibrium or this net ionic equation is not a Ka equation. This is a Kb equation because it has OH minus in it. The only time that we can use Ka to represent a net ionic equation is if there is H plus or H3O plus in the product side of our reaction. We can't use it here. And we have OH minus, this is Kb. So it's like, what do you do? Why can't I use this? They gave it to me. Well, they give it to you because this is an actual value for HF and it's related to it. And the thing about it is that we are going to actually have to use that Ka to figure out Kb. And the relationship between the two can come in one of two ways. And it's really related to water. Kw is the equilibrium constant for water is equal to Ka times Kb. It's the same thing that we had for concentration of H plus times the concentration of OH minus. And it's equal to 1 times 10 to the negative 14th, sorry. And so if this is what Kw equals, and if I know my Kw, which is constant, and I know one of these things, either Ka, Kb, H plus, or H minus, I can solve for the other thing. And so here's what we're going to do. Whoop. And we know this is 1 times 10 to the negative 14th is equal to my Ka, it's 6.6 times 10 to the negative 4th. The only time that you can really convert between Ka and Kb is if you're dealing with equations of your conjugate pairs. So this is relating HF and F minus. That's my conjugate pair. Yeah, I can do that for this. And times my Kb. So I need to solve for Kb, and it's done by dividing by each side by 6.6 times 10 to the negative 4th. And if I do that, I get my Kb value is equal to 1.515. I'm going out a couple more sig figs, times 10 to the negative 11th. And that's my new Kb value. That's what I got to use. And I can use it with this equation because it ends with OH. I can relate that to my expression because Kb expression for this is equal to products over reactants. It's your HF, concentration of HF, times the concentration of OH minus divided by the concentration of F minus. That's the stuff that we got from here. Your products divided by your reactants. And then it's all to the first power because all of these have a coefficient of 1. But now I can put in my equilibrium values into my expression and solve for this. So this 1.15 or 515 times 10 to the negative 11th is equal to, I'm going to put numbers or my values in here, X for HF, X for OH minus, and 1.20 minus X for the F minus. I can take out the minus X because my equilibrium value is much less than times 10 to the negative 4th. So I can assume that this is negligible. I can multiply by 1.2 on both sides and then take the square root. I will get my X value is equal to 4.26 times 10 to the negative 6. Now this value, I want to check the unit for it. Is it moles or molar? Because ice tables can work in either one. I wrote out what unit that I had at the beginning, and so that's my clue, what I was using. It's molar. So, yay, we solved for X, but we're not done answering the question. They asked us for the pH. This pH, it's like X, how do I figure out pH? I need concentration of H plus, or I need to figure out things like pH from POH, all that stuff. Oh yeah, I can figure out the POH because this X value is the same as the OH minus concentration. And then I can figure out pH. So it's like a little puzzle that you're doing, but I'm going to figure out my POH. It's equal to the negative log of the concentration of OH minus. Because that's what I just solved for X, it's equal to negative log of 4.26 times 10 to the negative 6. Huzzah! And that's equal to 5.37. So now I'm going to try using sig figs because here I started off with 3 sig figs here and 2 sig figs here. Because through my calculations, I should have 2 sig figs. Here my POH, I'm going to leave with 2 sig figs. Remember, POH and pH is really weird. You're only counting the numbers after the decimal for sig figs. It's weird, but it's logarithms. That's how it works. And then, because I have my POH, I can solve for pH. And POH equals 14. So 5.37. I subtract that from 14 to figure out my pH. And here my pH comes out to be 8.63. Huzzah. And so yeah, hoofta, that was a lot. This Ka and Kb thing, that is the biggest pain in the butt. But this is why we write out our net ionic equations to begin with. Write your net ionic equations for something. You have what you started with, interacts with water to form your products. This informs you of, are you dealing with the concentration of OH minus or a concentration of H plus that's formed from this thing that you started with. Because if you end up with OH minus, you are dealing with Kb. If you write out your net ionic equation, you end up with H plus or H3O plus over on this side, you are dealing with K and you can use a Ka value. But you need to be able to go between those two values, and it's linked with this Kw. Kw is equal to 1 times 10 to the negative 14th. It's equal to Ka times Kb. It's also equal to concentration of H plus concentration, or times the concentration of OH minus.